Okay, while classical assumptions 1 through 6 allowed us to claim that ordinary least squares was going to give us the minimum variance and on average correct, that is to say, best and unbiased estimates among all possible alternative estimation techniques. The seventh classical assumption is not really going to do anything like that. What it's going to do is open up the world of hypothesis testing for us, which means that it's going to enable us to make some statements about the population parameters based on the estimated population parameters, and we're going to have a sense of how reliable or unreliable they are. Okay, so that's where we're going to go next in chapter 5, and it's really this assumption that sets us up for that. Okay. So the assumption itself is that the error term is going to be normally distributed. Okay, the error term is going to be normally distributed, and we know that the normal distribution has this sort of bell-shaped curve kind of appearance, right? And if we add the classical assumption that the stochastic error has the mean of 0, okay, then this is also true if we're looking at a distribution of sigma values here. Okay, the two distributions shown differ not only in their means, this one at 0, this one at 2, but this one has a little bit thicker tail, and a little bit lesser tail and a little bit higher peak, which means that its variance is a little bit smaller than this one. This is the one with the thick tails here. Okay, a thicker tail distribution means that you're more likely to draw randomly an observation that lies farther from the mean. Okay, the more peaked this distribution becomes, the greater the probability that you'll draw a value close to the mean of the distribution. So that's what the normal distribution means. How unreasonable is it to assume that the epsilons are normal? Well, not as unreasonable as you would think. You'll recall that we talked about the central limit theorem back in our statistics conversation. And we said that if the influences contained in epsilon are many in number, small in size, and independent of one another, then it would be the case that the epsilons themselves would be normally distributed. Okay, so we're going to start here by writing down our model, right? And in this case, it's going to be y is beta 0 plus beta 1 xi plus epsilon I. And assumption 7 says that we're going to assume that epsilon is a random variable that has a normal distribution. Okay? It's going to be distributed normally. We sometimes use this little tilde sign here to mean distributed normally. Okay? So that's what this is going to be. We're going to take advantage of a theorem which says that a linear function of normally distributed random variables is itself normal. Okay? So we're treating, in this case, the beta 0 and the beta 1 as constants. We're treating the x as a set of constants. And so what we have is some constants added to a random variable that has a normal distribution. And so we can use this theorem and conclude then that if the epsilons are normal, it must be the case that the y's are also normal. Okay? Now, why do we care if the y's are normal? Well, let's go back to the ordinary least squares formula for the beta 1 hat. Okay? So the beta 1 hat formula that OLS produces when we solve that fancy calculus problem is exactly this. We're treating the x's as constants, we're treating the x's as constants, and what we have here then is a linear function of y's and y bar. And y bar is just the summation of y's divided by n. So the beta 1 hat itself is a linear function of the y's. The y's are now normal because the y's are a linear function of the epsilons. Epsilon normal, y normal, y normal, beta 1 hat normal. Okay? So we can make the claim that in repeated samples, if we continually generate new samples and continually estimate our beta 1 hat values, they will line up in a kind of normal distribution. Okay, this is not a terrible time to recall what the significance of classical assumptions 1 through 6 were. Okay, if these are not stochastic error distributions, but they are instead beta hat distributions, okay, and if the true beta equaled 2, for example, so this is the true unknown beta, then this could be an example of a beta hat distribution that was generated when the classical assumptions were in fact met. So if our true beta is equal to 2, and this is the distribution of beta hat values that arose in repeated samples and repeated computations of beta hat, then the fact that it's centered on the true unknown beta would make it an unbiased estimator. That's what unbiased means. Okay? If, on the other hand, the true beta were in fact 2, like this, but our estimates of beta hat look like this, they would be centered on the wrong value, and in fact we would say that there is bias in our estimator because on average it's producing estimates that are too small relative to the true value. Okay? So that would be an example of bias. Similarly, we have a smaller variance of this distribution, a larger variance of this distribution. So in addition to this one being centered on the wrong value, the fact that it produces a larger variance means that the probability of finding or obtaining a beta hat that lies farther from the mean is greater. Okay? And if in fact our classical assumptions are satisfied, we can be confident that our estimation technique, least squares, produces the minimum variance available among all other alternative estimation techniques. In symbols, we sometimes write unbiasedness this way. Okay? This is another way to say that the expected value or the mean of the beta hats that would result in repeated drawing of samples and the repeated calculation of the beta hats. Okay, the mean of that distribution is equal to the true unknown beta. Okay, and this is unbiasedness. If the expected value of beta hat is in any way unequal to the true beta, if it can be shown that that's the case, then we have a biased estimator. On average, our estimates are going to be too big or too small. So what we desire in our estimators, in fact, is unbiasedness. We also desire minimum variance because centering our estimates on the true value but with a very, very high variance means that the probability of drawing a value in any given sample that's far from the true value is very high. And so we want the smallest possible variance that we can get. Okay? How do we get a smaller variance? Well, among other things we can, because of the property of consistency, is we can actually increase the sample size. And our ordinary least squares has this property called consistency, so if we expand the sample size, the variance of our distribution of beta hat values is going to shrink, and the probability of our estimate lying close to the true value is going to grow. This is just another diagram which I believe is in your text that's going to give you another way of looking at it. Here's our true beta. Okay. Here is a larger variance of the estimates of the beta hats. Okay. Here is a narrower or smaller variance. Both are centered on the true beta, and therefore we have unbiased estimators, one with a smaller variance, one with a larger variance. Here we have a biased estimator because it's not centered on the true value. Okay? And here is the property of consistency. Okay, so the property of consistency is that as you raise your sample size, you are going to get a narrower band of estimates, a smaller variance, greater probability that it lies near the mean. Okay. All right. So we're going to introduce the standard error of the beta hat distribution. As it turns out, the standard deviation and variance of the beta hat estimates is typically unknown. So when we run an ordinary least squares regression, a computation is made that will generate an estimate of the standard deviation of the beta hat estimate distribution. Okay, so although we can't observe the true sigma or the true sigma squared, that is the variance of the distribution of the beta hats that would be generated if we could repeatedly collect samples of data and repeatedly estimate our beta hat. We don't get to observe that standard deviation. We do get an estimate of it every time you run a regression. So the column next to the estimated coefficients is going to contain the estimated standard errors. And that's going to be instrumental when we move into Chapter 5 and start to test hypotheses. Okay? If we increase the sample size because of the property of consistency, typically our estimated standard error of the beta hat distribution will fall. Okay? And that we think is a good thing. So we're going to be constantly trying to add more data to our data sets in order to get better estimates of the true beta parameter.